Okay, hello everyone. I hope you can hear me correctly. Welcome to the meeting of the Sixth Law Working Group. My name is Carlos Gomez. The other chair is Shweta Bandari. Our responsible AD is Eric Klein. We hope Eric will join soon. And for today, we have 1 minute taker, Georgios Papadopoulos, kindly will help in taking minutes. However, is there anyone else who would maybe like to volunteer to help Georgios in taking minutes?
Yeah, I'm on the eve of bed as well. Hi.
Thank you very much, Dominique. This is much appreciated. Okay, so yeah, please recall everyone that the process of taking minutes will happen over the Etherpad by using CodeMD, so anyone can also join and contribute to the collaborative process of taking minutes. So on the slide, you can also find a number of pointers to useful resources, such as the online agenda, the Java room for Sixth Law, the Meet Echo, which we are using, and the link for CodeMD for today's session. Okay, next please. Perhaps there's the notewell. Yeah, thank you. So yeah, this is the notewell. So recall that it contains a number of pointers to IETF policies on a number of important topics. So please make sure that you have read it. Next, please. This is the agenda for today. The first slot is the usual chair's introduction and presentation of draft status. So this is the presentation that's currently in progress. And well, after that, there will be the presentation of the last update of the applicability and use cases draft. That will be followed by the presentation of a new draft entitled Transmission of SHIC Compressed Packets over IEEE 2.15.4. That will also be followed by yet another new draft entitled Native Short Address for Internet Expansion. And finally, we'll have a presentation on Syslopan fragment forwarding and the use of forward error correction. So, as you can see, we have a total agenda time of 60 minutes. So we have a packed agenda today. And by the way, this is the first Sixth Law meeting in many Sixth Law meetings that we are going to dedicate most of the agenda time to discussing new materials. Well, are there maybe any questions or comments on the agenda? Okay, so let's move to the next slide. Thank you. So about the status of the working group documents, since the last IETF, we have a new RFC, that's RFC 9034, which is entitled Packet Delivery Deadline Time in the Routing Header for Sixth Law PANs. So congratulations to the authors, and thank you very much to everyone who helped and contributed with comments and reviews. So thanks again to everyone involved in the process. Other than that, we currently have 4 working group documents. The first one is IPv6 over NFC. So you may recall that this document was first evaluated by the ISG a couple of years ago. And well, after that, and the authors collaborated with the Shepherd to produce some updates of the draft. And currently there are some ongoing discussions on how to proceed, about the process of how to continue the evaluation at the ISG level. So I don't know if maybe if Eric joins later, our AD, perhaps he may provide additional details on this. But anyway, this is to let you know that there is some ongoing discussion about how to proceed with the next steps. The next document is IPv6 mesh over BLE links. This document was also evaluated by the ISG, and there was, after revision 9, there was one outstanding discuss, and the authors updated the document, and the discuss was clear. So currently there are no more remaining discussed ballots. However, there were recently some ISG members who stepped down. So as a result, now we need to have few more ballots to get the approval of the document. And we expect to have such ballots in August or perhaps early September. Then the next working group document is IPv6 over PLC. This document entered the ISG evaluation state quite recently, just around 1 week ago, and it is on the agenda for the telechat for the 12th of August. So in about a couple of weeks, we expect to receive the feedback from the ISG. And the last working group document is the 6LoW use cases draft. There was a set of comments which were received after the second working group last call for this document, and the authors have updated the draft, produced version -11. So yeah, there will be a presentation on this last set of updates today. Okay, so is there any question, any comment? Okay, so if there are no comments, then we may proceed to the next presentation, which is precisely about the use cases draft.
Okay. Hello, could you hear me?
Yes, I can hear you.
Okay, thank you. Okay, nice to meet you again. My name is Yonggun Hong. Today I'll present the 6LoW use case draft. Next page, please. Yes, this is the history and status. We have two working group last call. So in the last meeting, based on the 10th revision, we will try to resolve the comment from the second working group last call. So I believe that we resolved the last of the comment from the second working group last call, but there are the remaining comment after the second working group last call. So in this meeting, I will try to resolve the other remaining comment. Next page, please. Yes, so this is the update after last meeting. So after last meeting, we got two comments. That is comment from Tero Kevenian, and the other is to comment from the direct. So I would like to thank to them. The first comment from Tero Kevenian is I received that after submission of the previous draft, so I don't have any time to reflect this comment in the draft. So the comment from Tero Kevenians are the four. The first thing is to consideration of IEEE standard 802.59.26 recommended practice, and the other is expression of the IEEE standard. The other is to order title of the IEEE standard, and the final is removing an explicit external standard. And the comment from direct is the minor, is the type of some IEEE standard. Next page, please. Yes, the first comment from Tero Kevenian is that the consideration of IEEE standard 802.59.2060 recommended practice. He says that this draft does not take into account the IEEE standard 802.59 recommended practice. The IEEE standard 802.59 provides multiplexing and implementation layer for the IEEE standard 802.15.4. So this document should also note that in some IEEE standard 802.15.4 networks, those might not be needed, and the method provided by the IEEE standard 802.59 could also be used. So actually, I have no knowledge of the IEEE standard 802.59, but I studied and I investigated the IEEE standard 802.59, as I believe that the comment from Tero Kevin is correct. So I changed the text. As you can see, it is noted that IEEE standard 59-2060 provide multiplexing and implementation layer for the IEEE standard 15.9. Okay, next page, please. The other comment is the regarding expression of IEEE standard. He said the proper way to refer to the IEEE standard is to use IEEE standard 8.15.4 or IEEE standard 1901-2010. So note that the standard between the IEEE and the standard number, and that there is no period after the standard. So I checked the draft and I found that there are some mis-expression. So in the whole text, I changed IEEE standard 4 to IEEE standard 8.4, and I also changed as he recommended. Okay, next page, please. The other comment is the older title of an IEEE standard. For example, IEEE standard 8.15.4, the original title is to, as you can see, part 15.4 row rate wireless person area network. And then in 2015, it is simplified in IEEE standard for low rate wireless person area networks. And it also simplified again in 2020 to IEEE standard for low rate wireless networks. So I finally changed the last one, IEEE standard for low rate wireless networks. Okay, next page, please. The final comment is that removing an explicit external standard. It is related to the thread text. So he said that I'm not sure current thread group use IEEE standard 8.15.4 26 anymore. There is any feature that was there in 26, but which are no longer in your new version. So he suggests to delete the sentence, the IEEE standard 15.4 26 and IEEE 8.15.4 2015 version of the specification are used by thread. So I delete the sentence. Okay, next page, please. It is the comment from the direct. Yes, it is the minor typo. So I changed it IEEE standard 1901, and I changed to IEEE standard 1901.1 and 1901.2. Okay, next page, please. Yes, as you can see, in this time, we don't give any change of the technical part. It is all, only to relate to the expression or some typo. So I believe that I resolved all comments during working group, second working group last call, and after the second working group last call. Okay, that's all. Thanks. Okay, is there any question or comment? Hi, Carlos. Could you hear me?
Hello. Yes. So
hello.
Tero is in the queue. Feel free to speak.
Right. So I was just pointing out that the 15.9 had just new version, or actually revision of the 15.9 was approved like a month ago or so. So now it's in the IEEE editor's queue. which will probably take a month or two or something like that. And there will be 15.9.2021 should be out like in a couple of months. It doesn't have any, the fragmentation and that kind of things are actually same. The major difference is that there is actually now support for 15.4y, which is adding algorithms, multiple, different key cryptographic algorithms for 15.4 and allows negotiation of those two.
Okay, thanks.
If there are no other comments, if you want to take this forward, any volunteers to shepherd this document through ISG process? Please feel free to reach out on the mailer or to Carlos and me to, if you want to volunteer. Otherwise, I'll be shepherding the doc. Thank you. So moving on to the next one, Carlos, want to go ahead?
Okay, hello again. So I'm going to present the initial version of a new draft entitled Transmission of SHIC Compressed Packets over IEEE 2.15.4 networks. My co-author is Anna Miraburo from Aclio. Next, please. First of all, let's take a look at the motivation for this draft. As this working group knows very well, RFC 6282 has been the basis for header compression in 6LoWPAN and also in 6Low. This RFC was designed for 15.4 as the target technology, and it has been adapted or reused quite extensively for relatively similar IoT technologies. So with this RFC, it is possible to compress a typical 48-byte IPv6 UDP header down to a size of 7 bytes. That's in the best case with global addresses. And on the other hand, last year, there was the publication of RFC 8724, which is a product of the LP1 working group. It's also known as SHIC, which is a framework which provides addition layer functionality. Basically, there are two main sublayers, header compression and fragmentation in SHIC. And it has been designed for LP1 technologies, which are even more constrained than 6Low or 6LoWPAN technologies we usually handle. So if we focus on header compression, SHIC is capable of compressing a 48-byte IPv6 UDP header down to a size of, for example, just 1 byte, again, in the best case with global addresses. And it is based on the use of static context. And the technique here is exploiting a priori knowledge of header field values. Next, please. We may also consider an application layer protocol on top of IPv6 UDP, like in this case, CoAP. And, well, there is no specific 6LoWPAN header compression for CoAP. So in that case, we may compress an IPv6 UDP CoAP header down to a size of 11 bytes, again, in the best case with global addresses and also in this case with no CoAP header options. And however, there is some specification on how to compress CoAP headers by using SHIC. And as a result, it's possible to compress an IPv6/UDP/CoAP header down to a size of just 2 bytes. So this header compression improvement leads to some battery lifetime improvement for devices that run on batteries. And that's, in this case, if we use those mentioned protocols on top of 15.4, theoretically, and in the most extreme case, it is possible to achieve a theoretical battery lifetime improvement by up to 40%. That would be also including a 3rd byte when using SHIC, which would be the SHIC dispatch that will be presented later. And, well, a disclaimer here is that, of course, the actual improvement will be lower, depending on various parameters and features, such as device hardware, and especially the sleep current consumption, MAC layer settings, application layer settings, payload size, and so on. Next, please. So, about the status of this document. So the document I'm presenting today is an initial version. It's a 0.0. However, strictly speaking, it is not really a 0.0 because it's actually an extended version of another document that was with a narrow scope, which intended to define just the SHIC dispatch. And here the scope is greater. The aim is to specify everything necessary to enable the transmission of SHIC compressed packets over 15.4 networks. Also, the aim is to incorporate feedback from previous meetings. Next, please. Well, here we can see two protocol stacks. The one on the left is the traditional 6LoWPAN based protocol stack, where, as you can see, the 6LoWPAN layer has been illustrated as two separate sublayers. The one on top is the 6LoWPAN header compression, the other one is fragmentation. This is on top of 15.4. And on the right, what we can see is the protocol stack that would be the result if we apply this change that we propose here. So you can see that the only change in terms of the protocol stack relates with the header compression part. So here we would be using SHIC header compression instead of 6LoWPAN header compression. However, to be clear, the aim is not obsoleting traditional 6LoWPAN header compression. The goal here is to provide just another way to perform header compression if that seems to be suitable or beneficial in some 6LoWPAN or 6Low environments. Then another comment is that, as you can see in the protocol stack on the right, we stick to 6LoWPAN fragmentation. That's even if SHIC provides also some fragmentation functionality. However, here perhaps there is not that much of an incentive to use SHIC fragmentation for a number of reasons. First, in terms of functionality, we've had the recent publication of the 6LoWPAN selective fragment recovery, RFC. So from that point of view, perhaps there is not much more that can be added by considering SHIC fragmentation. Then also in terms of the size of the fragmentation header, it's not so clear that there will be a huge improvement from that side as well. And perhaps it's also positive to be able to reuse existing code, existing 6LoWPAN fragmentation code for implementations over 15.4. So as you can see currently in the draft, what we specify is that 6LoWPAN fragmentation would still be used. Next, please. So here we show the frame format, which corresponds to an encapsulated SHIC compressed packet. This would be carried as layer 2, meaning 15.4 frame payload. And there are a number of fields. The first one, that is the leftmost one, is the SHIC dispatch. This is a field which is intended to signal that what comes next is a SHIC packet, which is a packet with a header that has been compressed by using SHIC. So here what we define in the draft is a 6LoWPAN dispatch type dedicated for SHIC header compression as the SHIC dispatch. So here we exploit RFC 8025 and we use the paging dispatch, which, as you can see, has a size of 1 byte, starting with 4 ones and then 4 additional bits, which indicate the page that will be used. Recall that RFC 8025 basically expands the dispatch type space in 6LoWPAN, and here, for the sake of efficiency, to keep low overhead, the aim is to just use dedicate a whole page so that we can have the paging dispatch as the SHIC dispatch. And in this case, because most pages are currently unused and assigned, we would aim to use page 2. So as a result, the SHIC dispatch would be the one shown on the last bullet here on the slide, which is a 1 byte bit pattern. So there is one pane in the queue. I don't know if you may have any question at this moment.
Hello. I have a question about the dispatch type value assignment. I'm not very clear about when to assign a whole page and when to assign a dispatch value in page 0. Because here I can see we use the whole page, but if we assign only one value from page 0, seems to work.
Well, the problem is that we would need to actually see if, well, look at the available and assigned space from page 0, page 1 perhaps, but the problem is that we would need to probably use more than 1 byte, okay? And on the other hand, the point is that there are up to 16 possible pages, and most of them are unassigned. Actually, there are only 2 pages at the moment actually assigned, and there's a third one that will be assigned, but there are still 13 pages which are not used. Well, out of those, 1 is experimental, but anyway, it seems like perhaps it might be suitable to allocate a whole page for this, considering that the aim here is to keep low overhead, just keep a SCHC dispatch of just 1 byte. That's the aim here. I don't know if Pascal is also on the queue.
I have the same feeling, Peng, actually. We are using 1 value in page 0 to just signal page 2. It's just 1 sequence of bits, which are taken from the first byte, just like any value in page 0. So if you're using the full page to just mean one thing, I mean, I would like to study if we can find any bit left in page 0 as opposed to assigning a full page. It seems to me like a good idea to look at. I'm pretty sure there are a few bits left.
Okay, thank you. Thank you very much for the comments. So yeah, we'll definitely take a look at this. Okay, so then I guess we may continue with the next slide, please.
Otherwise,
okay, so then after the SCHC dispatch, what comes next is the SCHC packet. As mentioned before, it would be a packet with a header compressed by using SCHC. Then there would be some payload, and if needed, there would be a last field, which would be padding, with the aim to align the size of the frame format to an octet boundary. Next, please. Then we have a section where which is dedicated to explain and specify how SCHC compression will be done for IPv6, UDP, and COAP headers in this case. And first of all, we need to take into account that SCHC header compression may be applied to different protocols or sets of protocols. That means that perhaps we might apply SCHC compression to only IPv6, or perhaps to IPv6/UDP, or perhaps to IPv6/UDP/COAP jointly. So for subsequent versions of the document, we may need to look at how we should support the different options here. And that relates with how we specify the use of what is called in SCHC ID, which would correspond to the base compressed header. Other than that, we state that IPv6 and UDP header fields must be compressed as per section 10 of the base SCHC specification, which is 8724. Here there's one detail, which is that there are 2 concepts in .rfc, device IID and app IID, which correspond to the context for which SCHC has been designed, which is an LP1 network architecture, where there's the device, meaning the small IoT device such as a sensor, and then an application server, perhaps receiving data from that device. And perhaps those concepts don't always translate exactly in the context of a 15.4 network. For example, in a mesh network, there could be interactions between two peers. So this is something that might need some adaptation, perhaps. And another point is that regarding CoAP, we state that CoAP header fields, if CoAP is used, and if compression for CoAP is used, those fields must be compressed as per sections 4 to 6 of RFC 8824. Okay, so next please. Well, thank you. That was everything. I don't know if there may be other comments or questions. Okay, so yeah, Guangpeng.
Opinion, I think SHIC is a very good compression mechanism here, and we need to. It's valuable to integrate the SHIC and the 6LoWPAN framework. So it's only a comment. I think it's very good. Thank you.
Thank you very much for the positive comment. Thank you. Any other comments?
No, not for the moment. I will have a look on this draft, Carlos. Thank you for this presentation. And I will come with comments over the mailing list.
Okay, thank you very much, Georgios. The feedback will be very much appreciated. Okay, any other comments? Yeah, so then we may proceed to the next presentation. So that would be Guangpeng.
Hello, everyone. Guangpeng Li from Huawei is speaking. Today, I'll introduce a new Internet draft to you named Native Short Address for Internet Expansion. Next page, please. Okay, thank you. 3 points drive me to research on NIC technology. The first one is an ongoing massive expansion of network edge that is driven by IoT technology. And the second one is many work has been done to address the foundational issues, especially in 6LoWPAN, 6Low, and LP1 working groups. The last one is there is still room to improve the solutions because of existing solutions shortcomings, which include inherited address allocation mechanism from IPv6 consumes more bandwidth and energy. And the second point is native IPv6 address is too long. Constrained IoT network devices cannot afford large routing table that limit the scale of the network. And then RPL-based routing makes routers consuming extra resource to advertise, store, and manage route messages, thus increasing complexity of network. And next page, please. So what we want to do here is to propose a new solution based on native short address, NSA. It will optimize networking of devices within LT domain while towards to the internet. And it depends on neither specific lower layer conventions nor centralized DHCPv6 server. And more, there is no routing table is needed anymore. Thus, eliminate route messages. And considering the most common route over network case, the NSA approach will have 43% header length reducing than 6LoWPAN. Here, I received the comments from Carlos about the best case of LoWPAN IPHC. And as per the RFC 6282, the best case would be 2 or 3 octets. But I want to clarify here. If we consider the common case and most common encapsulation should be 7 bytes here. Okay. Next page, please. So next, I will explain what is NSA. Now, it's defined as a distributed assigned network layer identifier for efficient routing, and it's normally local affected and using a smaller address space than IPv6. Here's 3 key techniques: NSA allocation and table-free routing. Then the last feature is address encoding that avoids context and compression. Next page, please. Oh, thank you. For NSA allocation, there are some assumptions here for NSA allocation algorithm. One is network nodes rules and style of their address respectively, and the relations between parent and child address. Under this, an example of NSA network looks like right figure. In next pages, I will give an example to explain how does NSA be generated. Next page, please. Okay, nodes in NSA network may stay at 4 states. One is node with no address, and the root node, forwarder node, or the leaf node. Next page, please. When a node, say node X, wants to request a native short address, it sends address request message to its neighbors. The message carries predefined role and the node ID information of node X. Next, please. Okay, a leaf and a white node will ignore and drop the message silently. And next. And the forwarder node or root will execute address allocation function to generate a new address for node X and send the response message to node X. Next, please. So the node X will receive many response from its neighbors, maybe, and it will accept the first valid response and use that address, then ignores other late coming responses. Next, please. So after the allocation, native table-free routing can be used. For instrument routing, we define some rule with priorities. We also give an example to explain the routing procedure. Next, please. Suppose there is a packet destined to 111.011, the light gray node, the deep gray node from the 1011 node, and the light gray node. Okay, at the source, rule 2 will be matched firstly, so the action is sending to parent the node with address 10. Next, please. And when the packet arrives 10 node, rule 4 matched firstly, so the action is sent to its parent, the root node, with address 1. And next, please. And at the root, rule 3 matched firstly. So the destination should locate in subtree of this node. And then we will calculate the direct child of of this node and send to the next layer child node with address 1110. Next, please. So at 1110 node, rule 3 matched again and send to the next layer child. It's 111011. And next, please. And the packets will arrive at the destination. Okay, this is an example for the table-free routing. Next, please. Okay, previous pages explains the procedure of routing in the domain. But for the packet traffic from between native and IPv6 domain, inward and outward traffic need to be identified. For in-domain nodes address, border gateway need to concatenate and deconcatenate IPv6 prefix and NSA. For outside IPv6 address, border gateway can maintain a mapping table between IPv6 and a short index for that IPv6 address. And then a gateway performs translation when packets pass through the gateway. Next, please. After the allocation and routing, we want to develop the packet header encoding, which is based on LowPan framework and reuse part of header compression definitions of 6LowPan. And there are 3 length variable headers encoding, including payload length, source address, and destination address. And next, please. And some specific values of the length variable field will be used to indicate that a longer field will be used. So this is the basic mechanism for the length variable. Okay, next, please. So above all, we can achieve some improvements. Includes simpler routing, eliminate context, and saving more bits in headers. So this is what I mentioned, the improving room. Okay, next, please. So here is about the IANA consideration, the new dispatch type assignment. NSA needs to request some dispatch type values. The ideal values is 16, but under the terms of college, we cannot use the 0101 0000 value, which has already been used by the broadcast. So here we have some modification here, and we use 0101 0001 to 0101 1111, and this values is suggested to be assigned for NSA according to current state of this registry. But by the previous discussion, if the new page can be used, I think the NSA dispatch type can be assigned to a new page also. So So here, I think we need more comments here. Okay, next page, please. What I expect next is some interest will be inspired by this document. Collaborations, comments, questions are all appreciated, and I also seek for 6low group can accept this work and maybe part of this document. Okay, this is my presentation. Any question, comments? Okay. I saw Pascal.
Yes, Pascal, please.
Yeah, please.
That this hierarchy coach has been tried a great many times in the past. It was exemplified by IEEE 802.15.5 standard. And that standard was actually a big failure. And the reason why it failed is because it did not survive the real world. For instance, if you have mobility, like you change your parents, then that causes the change of address. If the structure of the graph doesn't match the number of children per parent that are expected, then the network cannot form. And there are a good number of reasons like that which caused 802.15.5 to fail. Some people came into 6low, I would say almost 15 years ago, proposing something similar. I think it was draft Daniel, high-low, something like that. And you will find in the 6low pan history that it also failed. I'm not encouraging 6low to try again, because we know this fails. Also, the way this draft is worded, it looks more like a layer 2 technology where you redefine headers and MAC than an IP technology where you can position IPv6. I don't even see why you're proposing those formats at the IETF. It doesn't look like an IETF piece of work, more like an IEEE. And again, like I said, it was already done at IEEE and it failed. If you want to look for more history, just take, for instance, 6low pan and hierarchical addressing, and you will find a number of papers which will show you all sorts of variations of these ideas in the past. But like I said, they all failed.
Okay.
Hello, this is Dominic. I want to concur with Pascal. I think this has been tried as well with the first version of ZigBee, if my memory serves. This was about 16 years ago. They had tree-based address allocation with ranges at each of the intermediate routers where you had to define statically the depth and breadth of your possible tree. And that was a failure. They quickly changed back to other addressing systems that are not related to the topology for the reason that Pascal explained. When the topology changes, then you have to renumber everything. That's my comment.
Okay, got it. About changes. Okay. That so the comments is about the when topology changes. What can be done by the NRC, right?
Yes, correct. You have to reallocate
Okay,
all
thank
the
you.
addresses.
I think it is a very interesting further research topic, and so I will update some sentences in the next version. Okay, thank you all.
Also, there's one couple of comments on the chat from Matthew Gilmore. One is +1 to Pascal's comments, and then a question which is how many client devices are supported with this proposal? Okay, perhaps one last comment. We are on the time for starting the next presentation, is that, also from the point of view of whether the work would fit in 6LO Charter, yeah, there is the concern that nodes in the NSA domain are not aware of their own corresponding IPv6 addresses, so perhaps that is a bit beyond or not exactly complying with IPv6, right? At least in the typical sense. So that's another point to consider. Okay, well, thank you, Guangpeng. So we can proceed to the next presentation on fragment forwarding and forward error correction in network coding. So Amohi, when you are free.
Well, hello everybody. I hope you can hear me well. And today, okay, great. And today I will talk with you about fragment forwarding and forward error correction, network coding, and propositions that, to our minds, could improve the reliability of the fragmentation with 6LoWPAN. So next slide, please. Thanks. On this small example, which is an example of forwarding of a packet under the RFC 4944 fragmentation mechanism, there are three main issues, some of which have been addressed by following RFCs. But the main one is that the loss of any fragment entails the failure of the full transmission mechanism. So if any fragment is lost, that will mean that all the transmissions that have occurred before will have been done in vain. So our concerns are how can we address this issue with new ideas and mechanisms. Next slide, please. So the fragment forwarding draft, the RFC 8930, has addressed some of the issues of the RFC 14944, mainly with the addition of the virtual reassembly buffer, which allows to avoid reassembling the packets at each hop. This has improved greatly the latency and the memory usage of the nodes, but still we have this one main issue that I just talked about, which is one lost fragment means that the whole packet is lost. And I will now propose introduce you to the forward error correction principle. Next slide, please. So forward error correction is, let's say, an idea in which, by adding redundancy to the transmissions that you perform, you aim at have a successful first attempt of transmission, so that you don't have to retransmit the full packet. In the RFC 8941, there is a different approach, which is let's make our first try, and with requests to the source node, let's correct the losses that we have suffered. The forward error correction principle is a different idea, where we really try to make the first attempt successful. So there are two types of FEC. The first one is the intra-frame one, where you aim at making the lost bytes of a fragment recovered through error correction codes that can be implemented into the fragments. But what we focused on is the interframe fake, where by adding new fragments, you enable the destination to recover the lost fragments, that you miss at the end. So we have three propositions of fake for 6-lopan fragmentation. And at the end, if you are interested, you can talk about one article that we found when we worked on this. Next slide, please. So the first fake proposition is quite simple. We called it XOR because it adds one additional fragment, which is generated by using the XOR, the exclusive OR operator on the original fragments of the packet. So thanks to this additional fragment, if any of the previous fragment is lost, it is possible to recover it by performing once again the XOR operator at the destination node. This entails the possibility of recovering one and only one fragment of the packet. Next slide, please. Thanks. So when a XOR fake packet is forwarded, we still use, in that case, the virtual reassembly buffer. And what we do is the additional fragment will have a datagram offset. A datagram offset that is where you add the payload of the size of the payload of the additional fragment, and all the fragments, including the additional one, are transmitted successively. And if the destination sees that one fragment is missing, but that it still receives the number of original fragments, it will perform the recovery by performing the XOR operator at the end. So that way you are able to recover one of the fragments that could have been lost. Next slide, please. So since the first fake mechanism was only able to recover one fragment, this next fake mechanism called rFake for retransmission fake will allow to recover more fragments. So it is very simple. Each fragment will be sent twice identically. So in that case, even if you lose the first fragment, next slide, please. Since you are also sending a copy of the first fragment, the relay node will be able to create the VRB thanks to the routing information contained in the IPv6 header compressed that is contained in this first fragment. The VRB will be able to be created, and the next fragments will be able to be forwarded. Next slide, please. So that way, as I said, the first fragment will be forwarded from the relay node to the destination node, and the second fragment will be able also to be forwarded. Next slide, please. And that way, even if some of the copies of the fragments are not received, next slide, please. We will be able to recover and to reassemble the packet as long as one copy of each fragment is received. And in case of reception of 2 copies of the same fragment, the second copy will be discarded because it will be unnecessary. So obviously this improves the reliability of the transmission, but also increases greatly the traffic. So we will now propose a new fake mechanism based on network coding. Next slide, please. So basically, it will start by fragmenting the packet as currently done by the fragmentation mechanism. Next slide, please. So the original fragments will still be generated, and there will be zero padding added to the last fragment. Next slide, please. And what will happen is we use an encoding algorithm based on finite field arithmetic, which have the important property where you only need the same number of original fragments to be received in order to be able to reassemble the packets. So in this example, we have 3 original fragments and 5 encoded fragments, and you can receive any combination of the of 3 of the 5 encoded fragments in order to be able to recover the packet. So this makes us able to have a lot more flexibility regarding the combination of fragments that will be received, and will increase the reliability of the transmission. Next slide, please. So then these encoded fragments will be sent, will be encapsulated inside the MAC frame. And in our experimentations, we just put the source address and destination address in each fragment. We didn't put the IPHC header, which is a mistake. If you want to be compliant with the 6-band fragmentation, you would add this field between the fragment header and the source address. But adding the source address and the destination address to each fragment allows us to be able to lose any fragment, including the first one, which with the current fragmentation proposal is the only one containing the routing information. And this makes it also possible in the future to have a mechanism where each fragment can be routing independently, and each fragment can be, for example, sent on a different path, which can entail interesting properties for our network. Next slide, please.
Sorry to interrupt. Yeah, if you could quickly finish, because we are past our agenda time.
Okay, I will quickly finish then. So in this example, we will have 4 original fragments leading to 6 encoded fragments. Next slide, please. And even if the first one is not transmitted correctly, successfully. Next slide, please. The second one contains the routing information, which will allow to forward itself. Next slide, please. And all the other fragments will be able to be forwarded thanks to this routing information. And any combination of 4 fragments would have enabled us to recover the fragments. In that case, it happens to be the fragments number 2, 3, 4, and 5, and we're able to decode these fragments in order to reassemble the packet. Next slide, please. So thanks for listening. If you have comments or questions, I will gladly answer them.
Yeah, so thank you for the presentation. We are past our agenda time. So we'll have, unfortunately, no time for discussing this today, but probably we can continue and we can discuss on the mailing list. And by the way, my understanding is that there is not yet an internet draft out there for this, but that you will publish one.
Yes.
Okay, so then after that, when you submit your draft, then it will be good to discuss on the mailing list. Okay, so if there is not any comment, maybe for a quick question or comment. Yeah, we are 3 minutes past our time, so probably we should say that the session is finished here, and hopefully let's see if we can see each other in person or virtually in Madrid. Thank you very much.
Thank you. Bye-bye.